the next thing that we're going to do is to solve some real world problems that involve exponential equations. And so we are going to look at Newton's law of cooling. Basically, if something is heated to a temperature, over time it will cool down, and how fast it cools down is based on several things. So your final temperature, and you do want to go ahead and take some time to label these. Your final temperature is just a plain capital T. Your initial temperature is T with a subscript of 0, and that's typically said as T naught. It's your initial temperature. The temperature of your room is T with a subscript of R. So notice you're starting with an initial temperature and you're subtracting the room temperature, which is going to be a cooler temperature. We have E, remember that's our natural base, and then we're raising it to the negative R times T power, where R is the rate of cooling for the substance that is being cooled, whether that's food, whether that's oil in a car, no matter what it is. T is the time that we let it cool, and then room temperature shows up one more time at the tail end. So let's take a look at an example and identify all the things that we know so that we can solve for what we don't know. So in this example, Lisa took a casserole out of the oven and measured the temperature to be 175 degrees Fahrenheit. So that's our starting temperature. Let's go ahead and fill that in here under our T naught, 175. The room temperature of her kitchen is 70 degrees Fahrenheit. Room temperature, T with a subscript of R. So let's fill that in as 70. After 20 minutes of letting the casserole cool, that sounds like time to me, 20 minutes, Lisa measures the temperature to be 135. So after that amount of time has passed, our final temperature after 20 minutes is 135 degrees. We want to find, well, the only thing that's left blank. What is the casserole's rate of cooling? So this is a big question mark. That's what we want to find. So let's go ahead and plug into our equation with everything that we know so that we can solve for the one thing, R, that we don't know. Final temperature, T, 135, is equal to 175 minus 70. Remember, that's T naught minus TR. E is a constant. Negative R is part of the exponent, but then we also are multiplying that by our time of 20 minutes. And then finally, we tack on our room temperature to the end, plus 70. All right, our goal is to solve for R. So we need to get that by itself. The first thing we want to do is go ahead and get rid of this entire extra term here. This is all one term, and we'll mess with it in a minute, that contains R, but this 70 is just tacked onto the end. So let's get rid of it. So subtract 70 from both sides. And that's going to leave me with 65, and that's going to be equal to, let's go ahead and do the math in this parentheses. 175 minus 70 is 105. That'll clean this side up a little bit. I still have E to the negative R times 20. And in fact, I could go ahead and kind of rearrange the way I write that and say negative 20R. Again, just kind of cleaning it up and getting rid of parentheses. Okay, remember that my goal is still to solve for R. E is the base where this exponent occurs, so let's isolate this next. And in order to do that, I need to get rid of the 105 that's currently being multiplied by E. Multiplication is undone with division. So I'm going to divide by 105 on each side. And that's going to leave me a decimal, and that's okay. Remember, we're working with real world problems. A lot of times we will expect decimals, and that's equal to E to the negative 20R. We still want to continue solving for R. And in order to do that, we need to get the r out of the exponent. We can't solve for it if it's in an exponent. And so we want to undo the base of e. Remember back a couple lessons ago when we talked about the fact that a exponent base of e and a natural log, which is a log with a base of e, will cancel each other out. So I want to take the natural log of both sides, because remember, anything that you do to one side, you have to do to the other side as well. So I'm going to say natural log of 0.619 is equal to natural log of e raised to the negative 20r power. And again, we are still trying to find r. However, now natural log and natural base are going to cancel and the exponent falls out. So I can say natural log of 0.619 is equal to negative 20 times r. And now I'm really super close here. I just need to divide by negative 20 on both sides to get r by itself. And so I want to go ahead and put this in my calculator. Remember that there is a special button, an LN button for natural log. So natural log of 0.619, close up your parentheses, divided by negative 20. And the answer you should get is going to be a decimal. It's kind of a small one. It's going to be 0.024, and that's in degrees Fahrenheit per minute. That's the cooling rate. Rate is the number of degrees per minute that it drops. Let's look at one little extension of this. We want to kind of go the other way now and say, well, now that we have a rate of cooling, let's figure out what the temperature would be a little bit later. So after 30 minutes, what will the temperature be? We now know that our rate of cooling is 0.024. Our final temperature is kind of what we want to know. We don't know that, but we do know that it's 30 minutes later. We still have our initial temperature of 175 and room temperature is still the same as well. So this time we are solving for, let's go back up here, we are solving for this number right here, a final temperature. Well, that's going to be easy because we're going to know everything else here. We're going to plug in all of these numbers and just simply plug it into our calculator to get T. So T is going to be equal to our initial temperature of 175 minus room temperature of 70. Remember that that's multiplied by E raised to the negative R times T, 0.024 times 30. And then tack on the end plus 70. Now, you can put this entire thing into your calculator as long as you are very careful to put parentheses where they go. Make sure you have a negative sign here. This is all in an exponent, and then be sure you come back down out of the exponent and put 70. Or you can do it in a few steps. It really doesn't matter. But once you put this in your calculator, and I do encourage you to double check this, you should get 121 degrees Fahrenheit. And I have rounded. I went and rounded to the nearest degree.